Okay, so today we're going to take a break from ecology and jump back into a little bit more of kind of river mechanics, talking about channel form and behavior. And so we're going to start to take a look at a little bit of the bigger picture of how rivers organize themselves. So rivers are like a lot of environmental systems. They react to kind of the inputs to the system. And so rivers will try to find a little bit of an equilibrium, as will a lot of environmental systems. And so when we say that rivers organize themselves, what we're talking about is rivers finding an equilibrium with the sediment inputs and the water inputs and climate and geology and a whole host of other kind of inputs and conditions. Rivers want to find kind of an equilibrium with all of those. And so the form that we see of any river in any place is kind of a result of the system trying to organize itself and trying to be the most efficient that it can. So one of the things that we need to talk about is what can a river actually change. So if conditions change, so if we get more precipitation that leads to more discharge, or if we get changes in our sediment supply, what can the river actually change? And so we generally talk about this in terms of kind of 4 degrees of freedom, so things that can actually change. And so the first degree of freedom that generally changes is the channel can change its width and depth. And we call this the cross-section dimensions, like we've talked about before. So if we get more water or less water, the river can change its depth or width depending on what's changing and how fast. The second degree of freedom is the channel slope. So how fast or how much, how steep the channel is can lead us to look at kind of aggradation versus erosion. The third degree of freedom is what we call the planform. So this is kind of the shape that you would see if you looked down from the sky or on a map. And so this is whether it's kind of straight or meandering or braided, lots of different types of different channel planforms. And some rivers can exhibit kind of all 3 of those, or there are other channel planforms that exist as well. And then the last degree of freedom is to actually change the bed forms in the river. So this is things like bars and riffles and pools. We'll talk about a little bit. We'll talk about this a little bit more in the next lecture too. But the actual kind of bed forms that exist on the bed of the river that lead to kind of a lot of the Manning's roughness values that we've talked about is one way that rivers can change. Is the last way that rivers can change as well. So one thing that's important here is that not all of these things, the degrees of freedom, can change all at once. Certain degrees of freedom will change faster than others, and this graph here shows kind of some of the ways that these degrees of freedom can change and kind of how big of an effect they have on the river system as well. So along the y-axis down here, we have the time scales, so from days up to 10,000 years. And then on the y-axis, we have what we call the length scale. So this gives us an idea of how big of an area might be affected by some of these changes. And so each box here shows a degree of freedom. And then the horizontal lines associated with that show you kind of the time scales over which that operates. And then the vertical arrows here show kind of about how much area of the river can be affected by these different changes. But primarily we're going to focus on the time scales here because that's really the important part. So our first degree of freedom in cross sections is the channel width and depth. And we're going to expect that to change potentially on a yearly basis with kind of annual floods. But more likely, we're looking at kind of maybe 5 years to change the channel width and depth substantially, and even up to about 50 years. Again, depending on how fast the inputs are changing and how much time the river has to react, we can see changes in width and depth anywhere from, less than a year all the way up to maybe 50 years. The second degree of freedom up in this graph is the bed configuration. This is the idea of changing the bed forms. And this takes a little bit longer. Width and depth are related to bed forms pretty intimately, but ultimately this is kind of on the 5 to maybe 100-year time scales. The next one up is meander wavelength, and that's just kind of a fancy way to talk about channel planform. And that takes significantly longer. And so now we're talking about maybe 50 up to 1,000 years, depending on how fast conditions are changing in the river. But generally, more than 50, probably averaging around 100 years to significantly change something like the channel planform. And then kind of the next one up here is slope. And so slope is one of the hardest things to change in a river, at least over long distances. But the time ranges here are really from about 50 years out to well over 1,000 years. And again, this is kind of really hard to change substantially over the river. And there's a lot of things that resist changes in slope. And then the last box up here, this idea of, we haven't really talked about this, but profile concavity or profile gradient is if you traced a profile from the extreme headwaters all the way down to the mouth of a river, changing the shape of that profile graph is kind of on the scale of landscape evolution. So we're talking well over 1,000 years, definitely, closer to several thousand years to change kind of the entire profile of a stream. So what are the controls on channel change? So the biggest ones here on the left-hand side are things like our drainage basin controls. So this is things like geology and climate, which is, akin to precipitation. So, geology really helps us control how fast we can erode, or, gives us a lot of information about the sediment supply. And then climate and precipitation lead to flow. And so these climate and precipitation give us the flow regime. So we talked about that. So whether it's, kind of a flashy system or a snowmelt dominated system or just rainfall dominated. And then also gives us the sediment regime. So how much, what are our sediment supply? How much, bed load sediment are we getting? How much suspended load sediment are we getting? Those all drive essentially the channel conditions and drive those degrees of freedom. And so we're going to look at a couple of graphs like this over the next couple days on the right here, or flow charts. And so this just gives us an idea of some of what we call the feedbacks. And so in this graph, the discharge of a river can be thought of as a little bit of an independent control. So discharge is not really going to change that much over kind of the time periods that we're talking about. But the way to follow this is, so discharge is kind of independent, and that drives what we call the velocity distribution in the channel, so how fast the water is moving. And then that velocity is going to drive the shear stress that's going to be acting on the bed. And that shear stress gives rise to bed load transport, and suspended load transport. And that then drives, so the transport of that sediment then drives channel form. So how much erosion or deposition we're getting in any one given area will change the channel form. And then the interesting thing here is that there's feedbacks back into velocity. So channel form then affects velocity, which then affects shear stress, which changes bed load transport, which then changes channel form, which then changes velocity. Okay. And then there's another inner loop in here too, which is things like selective transport, which we've talked about, and the availability of sediment and bed roughness, and that affects velocity distributions. And so diagrams like this are helpful to try to understand how things change in a river, because basically it's a little bit of a circular argument or circular system, in that we're getting feedbacks that velocity is changing shear stress, which is changing sediment transport, which is changing erosion and deposition, which then leads back into velocity. And that, just keeps going around and around and around. So that's something else to kind of keep in mind here, is that, when we're getting changes in the river, things that change in the river are going to kind of cascade into other changes, further downstream or even in the local area. Okay, so one way to kind of conceptualize some of this change and how the river might change over time is to use what we call the Lane sediment balance. And this was developed back in 1955 as kind of a conceptual model of how water and sediment and things like stream slope are affecting basically erosion or aggradation, and in what direction the river might change if we change any of these variables. So if you think about like this is kind of an old school kind of weight balance. And the idea is that the river's trying to reach an equilibrium between all of these things. We want this balance to be level. And so the things that the Lane balance takes into account here are the same things from this the slide before. So the flow regime and the sediment regime. Okay. We can think about the sediment regime being the left side of this balance. So this is our sediment discharge rates and our sediment size, which generally we think about as our median grain size, our D50. And then the right side here is our flow regime. So things like slope, which impacts velocity, and our discharge, our Q for discharge here. So discharge and slope on one side, the amount of sediment or the sediment discharge, and our median grain size on the left here. And so the equation that comes with this is down here at the bottom, is so that we're trying to reach a balance here. And if we reach a balance, we're not going to have overall erosion, and we're not going to have overall aggradation building up of the channel. And so the way that this reads is we have our QS, so that's our sediment discharge, times our sediment size. The symbol in here is proportional to our water discharge and our channels times our channel slope. Okay. So I've written that out down here a little bit more, is that so sediment discharge and D50 is proportional to water discharge times slope. And so the ultimate thing that most rivers are trying to get to by changing all of those degrees of freedom is to try to balance this equation, essentially. And so what we're trying to get to is sediment discharge and sediment size is equal to the amount of water and the slope that is present in the river. And so the way to kind of conceptualize this a little bit more is to think about if we got out of balance. Okay, and there's lots of things that can drive the system out of balance. So if we change the D50, or we change the amount of sediment, or we change the amount of discharge, or we change the slope, okay, that's going to tilt the balance to the left or to the right, depending on what we're changing. And if you look in the middle here, what you see is that if we change any of these things, if we change the slope, okay, we're going to get degradation. Or if we increase the sediment supply, we're going to get aggradation. Okay, so the arrow here is going to swing one way or the other depending on what we change on either side. Okay, and so I'm not going to go through all of these. I'll let you guys you can pause this video and kind of go through these individually to look at these, but we'll go through a couple examples here. So just as an example. So if, let's say we increase the sediment supply or the sediment discharge in a river, okay, that would generally lead to aggradation. That would kind of tilt the balance to the left. And so in order to rebalance the system, okay, we're either going to need more water or a steeper slope or potentially a smaller D50 would be one way that we could do this as well. Okay, so that we could change any of these three things, or most likely change all of those things, in order to try to balance that kind of increase in sediment discharge. So the thing to think about in some of these kind of hypotheticals, and I've gone through and kind of done, if we increase, and on the next slide we'll look at some decreases, what's really feasible? Can we get more water into a channel? Probably not. So this one's kind of out. So our real likely scenarios here are that we're going to either have to increase our slope to be able to move that much more sediment, or somehow get a smaller sediment size, which might not happen either. So in this case, slope is probably our best bet to change this. Okay, and I'll let you guys go through these other ones to kind of think about conceptually what might happen. But on this slide, we'll say, let's say there's a decrease in discharge. So we're decreasing our Q. And so in order to balance our equation, okay, we're going to need less sediment, okay, which is actually fairly likely since we have lower discharges. We're not going to get as much sediment discharge, so that might kind of help. We could go with a smaller D50, okay, which again, with less water might happen, but might not. So the sediment that's already in the system, if we get a lower discharge, is probably going to stay in that system. Or we could increase our slope in order to kind of balance. And so in this case, less sediment discharge is probably what's going to happen, most likely. Okay, more slope with less water is not going to happen, because we're not going to have the energy to change slope if we have a decrease in discharge. So in this case, less sediment is probably going to be the way to balance this out. Okay. So the trick, though, is that if something changes in the system, it's not always going to be balanced. Okay, there are certain situations in which we might swing the system too far out of balance. Small changes could be adjusted for, but sometimes larger changes can cause things to go completely out of whack. And so, this balance is quite sensitive, okay? And if we change too many things, we're going to get things get out of whack pretty quickly. And so on the next couple slides, I'll show you some examples of that. So if things get too far out of whack, okay, we're going to end up with the balance being kind of tilted to the left or to the right. And we're going to either get aggradation in the environment. So this is, where our deposition is going to outpace our erosion. So we're actually going to start to kind of build up the stream channel, or build up the floodplains. And so, there's definitely some causes for this. So if we decrease our shear stress or stream power, okay, and then we lose our transport capacity, we could get more input of sediment, okay, and that's going to lead to, not as much ability to transport that material, okay. And so there's lots of different forms of aggradation that can happen. So we could get bed aggradation if we get things like a lot of sediment inputs. We can do floodplain aggradation, both bed and floodplains. And then aggradation usually kind of comes with a planform change as well. And that we often we start to get a braided channel if we get out of whack towards the aggradation standpoint, because we're getting kind of too much sediment and not enough water generally, and that's going to lead us to more of a braided channel form. On the degradation side, where erosion is outpacing deposition, a lot of times this happens when we get an increase in shear stress or stream power. So changes in things like land use, which we'll see in just a minute, can lead to water moving faster through a system and can increase shear stress and stream power, and that can cause erosion. And sometimes if we see a lack of sediment input into the system, we can see a situation where a stream can be what we call sediment starved. And so it's got a lot of power and it's not releasing any of that on transporting sediment. And so it becomes kind of a hungry stream and it wants to erode in order to kind of expend some of its energy. And so the forms that degradation takes are things like incision. So this is where the channel can actually cut into the landscape pretty severely. We can also get a situation where, depending on things like geology or some of the other controls on the channel, we can actually get a widening of the channel or some combination of incision and widening. Okay. So the two examples here show incision. Okay, and this is one example on the left is from Kansas, and the example on the right here is from Iowa. And so these are where we're seeing the stream in size because we're a little bit out of balance. Okay, we've got a lot of water potentially, or changes in our water or our slope, and it's leading to kind of decreases in sediment, but then we're getting out of balance into the erosion side of things. And so the big thing here, these are both agricultural landscapes, and this is not something that's uncommon in agricultural landscapes, is to see stream degradation like this. And so just to give you an idea of scale, on the right-hand picture here, back at the back here, there's a gentleman in a white shirt kind of standing at the top of this. This is a gully erosion feature. And so that's at least maybe 2, if not more, person heights tall. So we're talking maybe 15 feet of incision here. On the left-hand image, probably not as severe, but definitely we're seeing erosion here. And so, the key here is that we're changing usually the amount of water that's coming in, and it's not slowed down by anything. So especially in agricultural landscapes where we don't have anything slowing down runoff, okay, that water can actually get up to a pretty good speed and start to erode. So we're kind of increasing our discharge and not balancing it with sediment or changes in slope. And so we're definitely well into the erosion side of that balance. Okay. Here's another example, and so you can see the person down at the bottom there to give you an idea of the incision in this landscape. It's very similar, okay, very deep, but in this case there's really no floodplain, and so we're kind of, the river's being forced to kind of dig in and try to accommodate the water that it's being given, and so it's doing that by eroding and changing its width and its depth here, specifically its depth, and we're seeing this pretty significant incision. So here's the land surface up here, and down, probably at least 15 or 20 feet down to the bed of the now bed of the river. Okay, here's an example of channel widening. This is from Australia. Okay, and again, you can see that there's been changes here to land use. Okay, so we either have an agricultural landscape, whether it be a grazing pasture or something else here. So you can see the forest in the background. That's probably what should be along the banks here, but it's not. And so we're seeing a lot of different changes here in sediment and water input. And so in this case, there is some geology here, so there is bedrock near the riverbanks here, and so it's preventing the river from going down, and so instead it's decided to go wider. Okay, in certain landscapes we can actually start to see kind of a landscape history of degradation as well. And so in a place like this is in Nepal, and what we can actually see here are a series of river terraces. So this is all the little lines out here, okay, and you can kind of see the steps in the landscape back here are all old river terraces. Okay, And then now the river is actually way down in a deep gorge here. And so this is a very kind of extreme example of kind of, again, on the landscape evolution scale of things, in that what we've actually done here on the balance is not change the amount of water or the sediment supply necessarily, but we've drastically changed the slope. So we've uplifted the Himalayas here. And so that change in slope has caused the river to start to erode into that changing slope to try to get back to some semblance of balance. Okay, but this is over a very, very long time period, that, hundreds of thousands of years to kind of actually achieve this. Okay, so if we go the other way, if we go into the aggradation side of things, okay, we can look at things like increased sediment supply. So in this case, this is from the South Island of New Zealand up in the Southern Alps. And so you can see the braided form here. So this is all sediment that's being released from glaciers upstream melting and depositing sediment into the valleys. And so that increased sediment supply has tipped the balance towards aggradation. The river is trying to adjust, but it's not doing a very good job, or it can't do so very fast. And so in this case, we're seeing an aggradation of the valley bottom here with all of the sediment. So we're actually building up the valley bottom because we can't transport out all of the sediment very quickly. Okay. Similar situation in a place like Denali National Park in Alaska, okay, where we see we can actually see evidence of both kind of past incision, but now modern aggradation. So again, you can see the braided planform or braided channel form down here. So we're definitely kind of building back up, we're infilling. But in the background here, you can actually see that there is an old river terrace. So there was at some point in the past, probably during the last ice age, there was a tip in the other direction that we actually saw incision, but now we're currently aggrading just because we're getting a lot of glacial outwash and glacial deposition in the river systems. Okay. Here's an example of aggradation in kind of a human-induced context. So this is in the Sierra Nevada mountains, and there are lots and lots of streams in the Sierras and throughout the West that were heavily impacted by mining. And so in the Sierras, especially during the 1800s, there was a lot of what we call hydraulic mining, where they were, using high pressure water to actually kind of wash out sand and gravel from the valley walls up and down these watersheds, and break up rock to do gold mining or other precious metals. And all of that kind of increased sediment supply from that hydraulic mining ended up in the valleys, and the river can't deal with it. And so in a lot of these cases, we've seen an aggradation because of the increased sediment discharge or increased sediment supply, and the rivers just aren't able to handle it, and haven't been able to handle it for several hundred years. And so we see this kind of landscape of, all this sediment, and then kind of a really, really small river flowing kind of on top, doesn't have enough stream power to do anything with it. And so we've ended up with this aggraded landscape. Okay. And so the last example is kind of a river at equilibrium. And so this is an example of the Sprague River in kind of south central Oregon. And this is a river at equilibrium. Okay. It's got a nice meandering planform, stable banks. Okay, it's got a balance of erosion and deposition. Okay, it's got a nice wide floodplain. Okay, and so this is a river in equilibrium, essentially, or essentially. And so we're not seeing degradation. We're not seeing aggradation. The river's just kind of at equilibrium. It's balanced. It's got the right width and depth and slope for the sediment that it has and the amount of water that it's being given. And so in cases like this, most kind of natural streams have found some kind of equilibrium. Okay, so the next thing I want to talk about in terms of channel form and changes in channel form is an idea called hydraulic geometry. And so the idea behind hydraulic geometry is that we want to try to look at how the river might change if we change something like discharge, since discharge is kind of one of our primary kind of independent variables. Um, and the original kind of sets of discussions and publications based on this idea of hydraulic geometry came out in the late 50s, early and late 50s. And so the idea here is that, again, that we want to try to predict how the river is going to change if we change discharge. And so the key kind of variables that hydraulic geometry looks at are width, W, depth, and velocity. Okay. And then all three of those can be related to discharge through three different kind of power regression equations. And so the the intercepts of the regressions here are set out as a, c, and k, and then the exponents for the regression equations are b, f, and m. And so one of the interesting things that has come out in a lot of the hydraulic geometry literature is that essentially when you do this, you should end up with intercepts. If you multiply all of those intercepts together, so if you multiply a, c, and k together, they should approximately equal 1. And then the exponents, b, f, and m, if you add those together, they should roughly equal 1. So this is kind of an interesting quirk of this way of analyzing how rivers are going to change over time, is that the exponent should add up to 1 and the intercept should multiplied together should equal 1. So the key thing here to remember is that the B, F, and M here are not mutually exclusive. And so the reason that these, if we add these together to 1, okay, is that if you think about the relationship between discharge and width, depth, and velocity, okay, if you remember way back to some of the first discussions about discharge, okay, discharge is width times depth times velocity. So these are not necessarily independent equations. There are definitely some crossover in how these things operate. And so just as an example here, this is from one of the original publications. This is on the Powder River in Montana. And so they've gone down the river at kind of pretty, kind of distant intervals and measured the width, the depth, and the velocity at those different kind of cross sections all the way down the river and plotted those out. And so in this case, you can see there's quite a bit of scatter, and we'll talk about that at the end here, but the scatter is not too bad. And so, but if you put a regression line through that, okay, on the width, we get an exponent of 0.28. On the depth, we get an exponent of 0.42. And on the velocity, we get an exponent of 0.3. Okay? And so what this is basically showing us is how fast these different variables, width, depth, and velocity, change with kind of in relation to, or change with changes in discharge. Okay. So in this specific example, we can look at the exponents here and say that, okay, F is the largest exponent. And so in this case, in this specific river, depth is going to change fairly quickly with an increase in discharge. Okay. And then velocity is the next highest exponent, okay, but not that far off from width. So width and velocity are going to change kind of more moderately, and depth is going to change fairly quickly with increase in discharge, okay, which is not uncommon in a lot of streams. Okay. And so the idea here, again, just to kind of reiterate, is that with an increase in discharge in every stream, you're going to see an increase in width, an increase in depth, and an increase in velocity. But how fast those change depends on kind of the local conditions, the regional conditions, climate, and a whole range of other things. Okay. So just to look at a few different types of rivers in a few different places. So the Great Plains in the southeast was done by some of the original work by two gentlemen called Leopold and Maddock. And so you can see here that the exponents are actually kind of similar to the ones we just looked at, but in the Great Plains in the southeast, okay, depth is going to change faster, velocity is going to change the next fastest, and width is actually not going to change very fast. Okay. Here's another one from this is Brandywine Creek in Pennsylvania. Okay, it's actually a gravel-bedded stream, and I think it's fairly confined in a valley. And so in this case, if we increase discharge, we're not going to see almost any increase in depth. That exponent is fairly small. We're going to see a moderate increase in depth, but we're going to see a huge increase in velocity. Okay, and that's just the nature of that specific channel. Out west, in the western U.S., okay, this is kind of down in New Mexico and Arizona, where we have a lot of sand-bedded rivers. Okay, we're going to see width change kind of moderately, depth change quite a bit, and velocity change kind of in the middle of those two. Okay. And so you can see that these exponents are kind of variable across different regions across the world, but that depth is usually the one that changes the most, and then velocity is the one that changes kind of next, and then width is kind of the least variable in this relationship. So that's looking at, so this previous example is actually what we call attestation hydraulic geometry. So this is if we look at kind of individual cross sections in a river. The next thing that we can look at is the idea of what we call downstream hydraulic geometry. So if we look at the relationship between width, depth, and velocity at the very headwaters of a stream versus all the way down at the mouth of a stream, there's another kind of relationship that we can kind of establish with that that's very similar to the attestation hydraulic geometry. Okay. But the interesting thing here is that with attestation hydraulic geometry, we're kind of just changing the discharge at a cross section. So, and that makes sense. In the downstream hydraulic geometry case, we're actually increasing discharge as we go downstream, and sometimes by quite a bit. And so this is a little bit of a different relationship, even though we use the same equations that I just showed you to kind of model how things are going to change. Okay. And so in this case, if we look at a similar set of downstream hydraulic geometry, so again, if we're looking at kind of a big watershed scale hydraulic geometries, okay, rather than attestation, we're going to see that the exponents actually kind of switch places in terms of their importance. So if we look at entire river systems in terms of width, depth, and velocity changing downstream, in the Great Plains in the southeast, you can see that actually once we start looking at whole rivers, the width actually is the most variable. So as we go downstream, we're going to get wider and wider and wider, which makes sense if you think about it. And depth is going to change kind of the next most. So we're going to get, essentially what this is telling us is that as we go downstream with more and more discharge in the river, we're going to get wider and we're going to get deeper. Okay. And then velocity doesn't actually change that much as if we go in the downstream direction. Okay. And that actually pretty much holds true for most streams in most places. Okay, width is going to change the most, depth is going to change the next most, and then velocity is the least variable. Again, if we're looking in kind of the big picture. Okay, and one interesting thing to note here is that why velocity doesn't change is primarily because as we go downstream, okay, we're getting more and more discharge, but our slope is actually decreasing. Okay, so we're actually, velocity, we're gaining discharge, we're getting wider and we're getting deeper, but because we're losing slope, okay, the slopes tend to be fairly shallow the lower down the stream we go. That's why the velocity exponent tends to not be as high as the other two. Okay. So some of the applications of downstream hydraulic geometry and hydraulic geometry in general, okay, are that we can try to predict if we have exponents from other places, or we can try to create our own for our own sites. But generally we use these as kind of like reference, the already established hydraulic geometry relationships as references to actually use to try to predict bank flow width and depth for a cross section. So we could take a random cross section on the Cedar River, and if we knew what the hydraulic geometry relationship should be, we can measure discharge and we can predict with a certain amount of accuracy kind of what the width and depth for that cross section should be. Another application of downstream hydraulic geometry in kind of the real world is that it's used a lot in stream restoration to kind of estimate what the restored geometry of the channel should be, again, based on discharges and based on some other factors. And then another thing that this can be used for is to kind of evaluate land use impact. So if you run a computer model with, a range of different land use scenarios, you can get kind of modeled discharge into the river. And if you know the hydraulic geometry relationships, you can estimate kind of how the river might change based on land use changes in a watershed. Okay. And so this is kind of an important concept because it really helps us show how width, depth, and velocity kind of vary through space. And it's shown, this has been done a lot in a lot of different streams all over the world, and it shows that a lot of streams have similar hydraulic geometry relationships. Okay. And what this shows, though, is that, because there's a lot of consistency in especially the downstream hydraulic geometry that we're seeing here, is that it supports the idea that most streams tend to be at equilibrium. If we found a stream that was not within a range of hydraulic geometry exponents, especially, that we would expect, you could potentially say that that river is out of equilibrium. Okay, especially for a given region or a space. And so that's another way that we can actually use downstream hydraulic geometry. So the question is, and the question that's come up a lot lately with as we begin to collect more and more data is hydraulic geometry real? And the answer is kind of, sort of, maybe. It's not a good answer for you, but downstream hydraulic geometry especially, holds true for most rivers, okay? And if you think about it in a general sense, if you think about the headwaters of a stream versus the mouth of a stream, the headwaters are narrow and shallow, and the outlet or the mouth of the stream is going to be wide and deep generally. Okay, if you look at the Mississippi River, okay, if you go up into Minnesota to the headwaters of the Mississippi, it's not that big. Okay, and then if you go down to New Orleans, it's gigantic. Okay, so in a real sense, hydraulic geometry is real. We can measure that change over space, and those relationships generally hold. The part where hydraulic geometry tends to falter is when we start to look at kind of higher and higher spatial resolutions and trying to predict kind of from one valley to the next, how is discharge and width and depth and velocity going to change? And that's where the relationships start to break down, because one of the things a lot of the relationships are established on kind of big picture measurements. So widely spaced measurements down a stream, and not kind of on the scale of reaches that we're used to mapping. And a lot of it really ignores the whole idea of complexity, which we've talked about. So, we're trying to predict width, depth, and velocity, but we're not really including any other factors like how much riparian vegetation is there, what's the sediment size, what's the, you know, the valley conditions. Is it a confined valley or is it a wide valley? How much, you know, is there a big floodplain or not a big floodplain? You know, is there lots of side channels or not a lot of side channels? Okay, is there lots of lots of large woody debris or not a lot of woody debris? Okay, so this is one of the pitfalls of hydraulic geometry, is that it really just kind of ignores complexity and is a little bit too simple for a lot of applications that it's used for. And so just to give you an idea of this, I think I've shown you guys the data that you're going to look at here already in class. This is my dissertation river in Eastern Oregon. Okay, and this is, you know, essentially a headwaters stream, but it gets fairly large fairly quick. And if we look at the data for this, so the top is elevation, so we call the longitudinal profile. And then we have drainage area on the next graph here. The slope, so this is actually measured every, I think, 3 meters downstream. And then the width, this is called the active channel width. So this is the bank, what we call the bank full width. So if we had our annual flood discharge, okay, how wide would the river be? Some other variables like sinuosity index, we'll talk about that in the next lecture. And then valley width. And then here is the estimated bankfull discharge. Okay, and on the bottom is an estimated depth. I didn't actually have enough I didn't have the tools to measure depth directly, but I was able to estimate depth along the entire length of the stream. And so this is 32 kilometers of river. And one of the things that you can see, okay, is that discharge increases at a pretty predictable rate. Okay, each of the little steps in here is a tributary. Okay, and there's a few bigger tributaries that come in, but discharge tends to kind of remain fairly stable going up. But what's interesting is that if we actually look at width in this graph, okay, it's not going up at kind of that same rate. Okay, it's fairly flat. There's some peaks and some valleys, okay, but it's changing at a much more kind of rapid rate than discharge does. Okay, so this would lead us to believe that hydraulic geometry, at least at this kind of spatial scale of a few meters of stream, you know, we're taking our measurements about every 3 meters downstream, width is actually changing a lot more than discharges. So in this case, hydraulic geometry doesn't actually work. Okay, those regression lines wouldn't actually be able to predict width because we're going up and down, up and down, up and down in here. Okay. And then there's some spots where we get really wide and then back to more normal. Okay, and then like down here we get really narrow where it goes through a little bit of a canyon section, and then it gets really wide on the downstream end. Okay, and of course some of that corresponds to changes in discharge, but not all of it. Okay, so a lot of this just has to do with the valley width, okay, the valley geology, and has nothing to do with the actual discharge. And similarly, if we look at slope, okay, as a hydraulic geometry relationship, okay, we can see that there's, you know, some big changes in slope and local changes in slope, but again, those you couldn't necessarily predict all of this variation solely from discharge. Okay, there's a lot more variability and a lot more complexity going on in here. Okay. And so I don't want to, this is a little bit of a scary graph that I'm going to show you next. But this is the idea of doing what's called a hyperscale analysis. And so essentially what we're going to do here is try to model or try to predict our downstream hydraulic geometry relationships by looking at the distance downstream, okay, which we're going to approximate as our discharge, okay, because the further downstream we get, the more distance we accumulate, which is just like discharge. And we're going to look at how width changes over that distance. Okay. And what we can do with this is we can actually calculate a regression coefficient for this relationship. Okay, so if we have, say, in this case, if we have 10 we're taking measurements every 10 meters downstream. Okay, and we measure widths at each meter downstream. Okay, we can plot all of those and get a regression line for those. So this is basically giving us the relationship between width and distance downstream, but that's just like our hydraulic geometry relationships of looking at discharge or width as a function of discharge. Okay, and so this is a fictional example, and so in this case we have a fairly weak regression slope. Okay, but the thing that we can actually do is we can actually start to break down and look at, okay, not just at all of the data, but we can actually look at the data in smaller chunks and kind of smaller overlapping chunks to see if there are kind of relationships at different scales. If we look at, instead of looking at the whole river, if we look at, say, 90% of the river, and then 80% of the river, and then 70% of the river, and all the way down. But basically, once we start getting smaller, we can actually look at what's called a moving window approach. So actually if we look at 90% of the river, it's the upper 90% versus the lower 90%. Okay, and if we go 50% of the river, we can actually kind of look at whatever the length of 50% of the river is and move that downstream in small increments and actually get kind of what are the relationships at that length scale all the way down the river. And so we can build these together into kind of a pyramid, which you can see down at the bottom. And the graph that comes out, again, is, I'll admit, a little scary, and I'll try to explain it a little bit more. But essentially what we're looking at here is at the top of the pyramid is all of the data. So if we go back to this graph, if we take all of the data for width here, and we look at what is the regression coefficient or the regression slope of a line that estimates all of that data. So in this case, we're going from kind of relatively narrow to fairly wide at the top. So if we did a regression through all of this data, what would the slope of that regression line be? And so we can plot that as a color at the very top of our pyramid here. And so in this case, our regression coefficient or correlation coefficient is about 0.6, which is actually pretty good. Okay. And so what this tells us, though, is that at this scale of the entire river system, width and distance or discharge are related. Okay, so as we go downstream, our width is increasing. Okay, that holds with hydraulic geometry. But what's interesting is as we start to go down the pyramid, okay, we're getting a smaller and smaller sample of widths and kind of moving those downstream. We actually can see that, especially once we get down past a certain point down here, we actually start to see some interesting patterns that are, in some areas, we get an increase in width as we go downstream, but then it switches to actually getting narrower as it goes downstream. So the blue here is a negative correlation coefficient, which means that it's not purely a positive relationship. We're not just getting wider as we go downstream, we're actually getting narrower as we go downstream. Okay, so if we look at like the 4 kilometer window size here, so if we take 4 kilometers of the river and do the relationship and then move that 4 kilometer window down and down and down and down, we're getting all of these different colors in here to represent these different relationships. And so at the 4 kilometer scale, we're getting an increase over a certain distance, but then the width decreases, and then it increases again, and then it decreases actually fairly dramatically. And then it's in the blank areas here, that's kind of not statistically significant correlation, so it's actually staying constant. And then in the lower part of the stream down here, it's getting wider, 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 but then it gets narrower for a section down here, and then it gets wider at the end. Okay. And then all the way down at the bottom here, you can actually see that it starts to alternate between red and blue very, very rapidly. And down at this scale, we're actually looking at, and we'll talk about this in the next lecture a little bit, is we're actually starting to see the bed forms of the channel actually come out. So at really, really small sample sizes, hydraulic geometry is completely useless. And so what this tells us is that if we look at the big scale, hydraulic geometry can be useful. Okay, of several tens of kilometers of data, we can predict width, depth, and velocity based on discharge, no problem. But once we get down to kind of smaller scales, which is more like the scale of most restorations projects, this is where the complexity starts to take over, and we're not actually able to predict very easily with the simple equations of hydraulic geometry what the width and depth and velocity should be. So it's something that's been shown kind of over and over and over again, is that if we look at kind of the larger scales, hydraulic geometry is fine, and that's kind of what it was designed for, but trying to use it for smaller scales tends to fall apart pretty quickly. Okay. And if we look at kind of the generic kind of downstream patterns that we'd expect for river systems, and this kind of goes back to the idea of the river continuum concept too, but if we start from the headwaters and go downstream, okay, so increasing drainage area, increasing discharge, okay, we see the different lines on here. You can see, so we get usually a decrease in sediment size. We start with coarser sediment in the headwaters and then have finer sediment out the end. Okay, we get a decrease in slope. Okay, we get a decrease in velocity because of that decrease in slope. Okay, but the lines in the background here that are increasing, so we get an increase in depth, we get a bigger increase in width. Okay, big increase in stream discharge. Okay, and then the other line in the background here is the amount of floodplain storage of alluvial sediment. So the further downstream we get, the wider the floodplains, the more sediment we're storing on the floodplain. Okay, so that's a good place to stop for this one. And we'll jump into a little bit more of channel geometry in the next lecture.